So imagine this, you walk into your room, find a pile of socks, notebooks, and files all jumbled together. But instead of sorting it one by one, you notice something. Some socks are already matched, some books are already in the right order, and in this scenario, some files are already stapled together. So what do? Instead of arranging them one by one, you start organizing the already sorted ones first, and then combine the rest into the neat groups. Without realizing it, you just sorted everything faster by working with what's already in order instead of starting from scratch. Believe it or not, this is exactly how one of the fastest sorting methods in the world works. Not just smart, it is a real world smart. This isn't just about laundry or library shelves. It's the same logic that powers major programming languages when they need to sort millions of records fast. In this video, we'll explore how real-world logic inspired the Timsort algorithm, how we simulated it, and what we discovered through our testing. Let's dive in.
Today, I will be discussing the Timsort sorting algorithm that is designed to recognize patterns in datasets. Timsort was introduced by Tim Peters in 2002 for the Python programming language. It eventually became the default sorting method not just in Python but also in Java through arrays that sort. The main strength of Timsort lies in its abilities to detect already sorted sequences called runs and process them efficiently. It means it can minimize unnecessary comparisons and swaps, which speeds up the sorting process, especially for nearly sorted data. Now, let's take a closer look at how the algorithm works. Timsort is actually a hybrid of two sorting methods, insertion sort and merge sort. For smaller datasets, Timsort uses insertion sort because it is faster and more efficient on small inputs. But when the datasets gets larger, the more complex, it switches to merge sort. This dual approach makes Timsort highly adaptable and efficient for real-world use cases. Additionally, it manages memory well and keeps low overhead, making it both fast and resource-friendly. So our next topic is time and complexity. Understanding the time and complexity of Timsort is important to appreciate how well it performs in different situations. Using big O notation, we can measure the best case, average case, and worst case scenarios. This helps us understand why Timsort is often the preferred sorting method in popular programming languages like Java and Python. Continuing, when we look at its time complexity more closely, Timsort performs very well with nearly sorted data. In the best case, its time complexity is O of n, which means it only takes linear time to sort the data. However, in the worst case, when the data is completely random, the performance goes up to O of n log n. This is still efficient and shows how Timsort cleverly uses insertion sort for small unsorted sections and switches to merge sort and needed for larger unsorted parts. This hybrid nature allows Timsort to perform reliably across a wide range of data types and sizes.
So, as we've seen in the previous slide, Timsort algorithm really has a capability to adapt to its complexity. This marks them is a good choice for any type of datasets because Timsort algorithm is hybrid. It has two mode, which is the merge sorting and the insertion sorting. In the bright side, Timsort algorithm is significantly improved in sorting. But if we look in the bad side, merging process can sometimes be a problem as it consumes extra memory. And by saying it's a problem, sometimes when working in a short memories environment, it can be considered as a problem since, like I was said earlier, it consumes extra spaces. So even though it is good inserting, really it also has a bad sides. But even so, Timsort algorithm is marked as a good sorting, and also it is a default sorting in many different languages.
So now we're going to discuss about the real-world simulation of the Timsort algorithm. So Timsort algorithm is good in every way. So we have here the example of the real-world situation is the e-commerce data. So okay, imagine you are managing an e-commerce platform like Amazon or Shopee, and you want to sort product list by price or rating. So and your data looks like this. So we have here our products, the name, the phone, the price, and also the ratings. Here's what Timsort algorithm does. First, they find natural runs in the product list that are already sorted by price or ratings. Second, is sort short unsorted runs using insertion sort. So we have the third and the last is merges all runs into a fully sorted list. So why Timsort is good for this? So we have the product data is often partially sorted. For example, new products are added at the end, but the rest is already sorted. So Timsort detects these sorted chunks and takes advantage of them. So it's fast and stable, does not change the order of items with equal keys. So as we all know, by conducting simulation, it is observed how Timsort algorithm adjusts its sorting strategy based on the input. So, because of its adaptability, the Timsort algorithm is popular choice for many applications.
So, test cases. There are two types of test cases for the sorting Timsort algorithm. The first is newly sorted datasets. So when we say newly sorted datasets, these are datasets that is almost sorted or like almost finished. Timsort algorithm will work at its best on these datasets because the datasets are almost sorted out. Let's put an example of 1, 3, 2, 4, 5, 6, 7, 8, 9, 10. So as we see, 2 and 3 is just swap in places. So Timsort algorithm will just sort them out easily. So this puts sorting algorithm at its best. The second one is reversed or completely unsorted datasets. These datasets are those datasets that is completely randomized or scrambled. So it's like a storm there. Like this will put Timsort algorithm at its worst since the datasets are completely randomized, reversed, and scrambled. That's why, if we think about it, Timsort will have a hard time in sorting these data sets out. So, to wrap things up, as we saw in the given example of real-world simulation and algorithm simulation, that Timsort algorithm works best when the data sets are nearly sorted or almost finished up being sorted, while it will work at its worst when the data sets are completely randomized, scrambled, and destroyed. So, this is the pros and cons of Timsort algorithm.
The performance evaluation of the Timsort algorithm shows the effectiveness, both its theoretical time complexity and its real-world simulation. This means we didn't just rely on what the algorithm is supposed to do in theory, we also tested it ourselves through practical implementation. By comparing both approaches, we are able to see if Timsort's expected performance, like its big O and log n time complexity, actually matches what happened when it's applied to the real data. This dual approach gives us more complete and reliable understanding of how well Timsort works, not just in textbook but in real-life scenarios also. The result of our Timsort algorithm test showed excellent performance when sorting data. It confirmed that the algorithm performs best in its big O of n time complexity, especially when the data is partially sorted. However, when working with large datasets, the time complexity can increase to big O of n log n. While still efficient, it naturally takes more time as the amount of data grows. Overall, our result shows that Timsort is one of the most reliable sorting algorithms for different kinds of inputs, whether the data is small, large, sorted, or random. One important observation during our evaluation is that Timsort requires additional RAM or memory during the merging phase. This is because, like merge sort, it needs extra space to combine sorted run, and limited resources can affect its performance. Timsort has several strengths that make it stand out as a reliable sorting algorithm. One of its key advantages is its predictable and consistent performance across different types of datasets. It also offers stability in sorting, which means that elements with equal values keep their original order. This is especially important in real-world applications where order matters, like sorting names with identical scores or date. According to SABA 2023, Timsorts perform well not only with different data sizes but also with various data patterns. This flexibility and adaptability make it a dependable choice for modern systems and applications. Despite its strengths, the Timsort algorithm also comes with a few limitations and challenges that are important to consider. One major issue is its higher memory usage during the merging process. Since Timsort needs extra space to merge sorted runs, this can be a problem in environments with limited memory resources. Another challenge is its complex structure. Unlike simpler algorithms, implementing or debugging Timsort can be more difficult. It takes more effort to properly manage how runs are detected and merged within the datasets. As pointed out in reference, these factors can mean that while Timsort is powerful, it also requires careful handling, especially when used in systems with tight resource constraints. Even with both advantages and limitations, Timsort still stands out among all sorting algorithms. Its hybrid approach, combining merge sort and insertion sort, gives a flexibility and adaptability needed to perform well in almost any situation. Unlike quicksort, which can degrade to big O of n squared in worst case, and Timsort guarantee a worst case time complexity of big O of n log n, and in best case, it can perform in big O of n time. What makes Timsort especially practical is that it takes advantage of naturally occurring order in real-world data. That's why it's not just another algorithm. It's a default sorting algorithm in major programming language like Java and Python. According to Wilboa and Faisal 2024, Timsort consistently outperforms traditional algorithms such as heap sort, shell sort, and even standard merge sort, especially when handling large data sets. Its ability to adapt to different patterns and sizes makes it the best option for any of the applications we rely on today.